Welcome again to the topic. So, we will continue from the last lecture. There were few outcomes of this particular course that we discussed yesterday, right. So, the first one, if you remember, if you recall, was you will have an understanding on the concept of quality. The second one was you will demonstrate an understanding on robustness. You will be able to formulate robustness, meaning quantify robustness and use it in a formulation for design. Okay. While performing design, whether conceptual or detailed design, you will be able to design a particular structure or a product or a component for robustness. Okay. And the third one that we talked about is the design of experiments. So, we will understand why a design of experiment is required in a design setup and what is the role of design of experiment in accomplishing a quality based design or a robustness based design. These are the three major outcomes that you can expect out of this course. The couple of things that we discussed yesterday kind of ticks off these bullets. Okay. The first one is about the quality itself, like how do you define quality. Then we did exchange views on how each one of us looks at quality, and then we gave the way in which Taguchi looks at quality. So, he essentially says that there are three components that come into picture. One is the customer, one is the manufacturer, and the other one is the society. Okay. So, if a particular product does not live up to the promise that the manufacturer makes or does not live up to the expectation that the user had, it is not only the two of them that are affected, but the third, the society, which could be directly or indirectly related to these people, are also affected. So, quality should be measured from that perspective rather than only a loss for either the manufacturer or the user. So, this is something that we saw yesterday, right. It appears that it is disconnected at this point in time, but today or in the next lecture we will be able to make the connection. You will be able to relate why we spoke about robustness. Okay. So, then we kind of discussed what robustness is. Robustness, directly put, what it means is irrespective of the variation in the inputs, my output variation should be minimal or it should be within the bounds that a particular or whatever the designer or the user specifies. That is what your robustness means. So, we discussed this example of a furnace where you make the tiles and there was non-uniform temperature was there. As a result of it, the size of the tile varied. So, that is a variation in the tile size, which is what is your output. The input variation was there was non-uniform temperature. So, irrespective of the temperature difference, the interest was to maintain the output dimension of the tiles. So, the important point in that robustness is you do not address the cause of the variation itself. So, you did not go and change the non-uniform temperature, that is not what you did, but still you address the effect of the cause of the variation. Okay. So, that is the point of the important significant point of robustness. So, you do not get rid of the source of variation, the source of variation is still there, but you still design it in such a way that your output variation is minimized. So, that this becomes important because in all the settings you will not be able to eliminate the source of variation, okay, but still your product's performance output cannot vary as much as it wants. Okay. It should be minimal or it should be within the limits that the designer specifies or the user specifies. Okay. So, if you recall, out of the three major learnings that we would like to have in this course or that I pointed out, the first one was about the concept of quality itself, that is something that we have seen. The second thing is an introduction, a verbal introduction to robustness. So, today what we will try to see is how you can quantify this robustness. As we discussed earlier, as engineers, whether you want or not, you want to quantify things. You cannot say, okay, subjectively this student is better than that student. I cannot say that, but there should be a metric for me to let me tell that this student is better than that student, this product is better than that product from functionality perspective, from performance perspective, from robustness perspective. So, you need a metric to measure robustness. Okay. So, today we will see what is a metric that was proposed by Taguchi to look into robustness, that is one thing. Okay. But before that, there were a couple of clarification that was required yesterday. One was we discussed quickly about the probability distribution function, the distribution function being thin or fat and all that. So, what we discussed yesterday was predominantly in this course we will talk about one particular distribution, that is the normal distribution or the Gaussian distribution, which is the bell shaped. Now, if you see the church bells, no, it is that shape. So, it is called the bell shaped curve, right. So, this has some very nice properties, because you can you just need to know two moments to describe a normal distribution, which is your mean and your standard deviation. Mean is nothing but your average. Statisticians call it expected value, because it is not the real, right. So, there are two terms in statistics, one is called the population and the other one is called the sample. Okay. The population is something that you would like to have, okay, which is the ideal case, but oftentimes you might not be able to get the population. So, what you will do is you will take a sample, okay, a significant representation of that population is what called the sample. So, oftentimes when you want to estimate the average, what you do is you go and estimate the average on the sample. So, now this average, you hope this average to be the average of your population. As long as your sampling was right, this will be equal to the, or it will be close to the population's average. That is why it is called the expected value. Okay. It is usually written as E of x, x means the variable that you were talking about, right. So, it is called the expected value. Okay. The statisticians, if you see, the word that they use is called the expected value, but the regular engineers and laymen, you can use the word average or mean. Okay. So, for a normal distribution, you need only two quantities to describe it. One is the mean and the other one is the standard deviation, right. So, in order to describe this guy, I just need the mu and I need the standard deviation. Okay. So, now, what does this standard deviation actually mean? Okay, that is something that we wanted to discuss. Okay. Now, let us say that I want to take the height of the students in this class. Okay. There are about 60 students and I want to have the height of the students in this class. So, it is an array of the height of the students, right. So, 6.2, 5.8, 5.5, 6.16, 5.2, I do not know, maybe 6. There are some height of the students, right. So, there are multiple ways that you can look at these information. Okay. If all of you were of the same height, then I do not need to worry. If someone asks me what was the height of the students in your class, 5.8, the job is done. But right now, if I step out of this room and someone asks me what is the height of the students in your class, okay, I will say, I am likely to say the average height is this. Okay. The moment you are going to have more than one output value, the usual metric that you start to use is the average. Okay. So, I guess I do not have to explain you what an average is, right. So, you know what an average is. So, it is going to be summation of, in this case if I will call height as x, so summation of this xi over the total number, that is your average. It is also called as average mean. The other one is a spread. This is called a, okay. So, this is more of a position. It says where your distribution is going to be sitting. Will it be here, will it be here, will it be there. Okay. So, that is described by your mean, and whether this distribution is going to be, fat, please understand it is at the same mean. the mean is the same, but my standard deviation is different in this case. Okay. My standard deviation is different in this case. Okay. So, if I have a larger standard deviation, then it means that it is a fatter distribution. So, we will see what it means, whether it is a thinner distribution or fatter distribution, how does it affect is important from a robustness perspective. So, we will discuss that one. Okay. But what exactly is this standard deviation? What does the word standard deviation means? Okay. So, the idea is I want to understand the spread of the data. Okay. So, if someone asked, okay, now you are teaching this design for quality course after you guys take the exam. If someone asked me, what was the performance in your class? So, I would say, well, the average was 70%, but this only tells you part of the story. What could be the other part of the story? Yeah, that is a specific information. So, he is asking how many people scored greater than 70 and how many people scored less than 70. That is okay, that is one another information. What else?
How close to 70?
Sorry?
How close to 70 the students?
So, how close to 70 did they? Okay. Okay, one is the distribution, the frequency of the scores, that is one thing. Then one easy thing, one trivial stuff. Okay. So, when a cricket player comes into the ground to play, some statistics come up. Okay. When he or she enters, on the screen you see some statistics which says that XYZ is his name, and then there is some statistics. What is that? One is the strike rate, the other one is the average score that he has done. So, that is the first metric that comes to your mind. Okay. So, strike rate is how much he or she is going to hit in 100 balls. Okay. That the rate at which, that is why it is called the rate, right. What else? What was his highest score? Okay. One thing which will look very negative, probably that is the reason that they do not telecast that one, is minimum. What is the minimum that person has got? Okay. So, why this is required is, you need to have an average score. So, I expect you to score that. What does that average means? If a particular batsman is coming into the field and then I project this number and I tell you that this is the average. What does that mean is, I expect you to score close to that average, this way or that way. But that is the meaning of average. On an average, this person is going to do that, which means on any random game that this person is going to enter, this batsman is going to enter, he is likely to score that, likely around that. Okay. But there is also a situation that this person has scored a maximum value. Okay. There is also a case where this person has scored a minimum value. So, oftentimes you need to know the range. Okay. There are this one classical book called How to Lie with Statistics. Okay. So, many times when you look at performance of a company or performance of a share, you might not want to see what is the average performance. Okay. You want to know what was the maximum that the share went and what was the minimum that the share went. That will tell you what are their chances of your profit or what are the chances of your loss. The company's performance, you need to look at those statistics. Okay. For instance, your gross domestic product, GDP, is an average metric. It is good, it is a good indicator, there is no point about that. Okay. But it talks only in an average sense. Okay. If your average is going to move to the right, okay, if your average is going to move to the right, that can happen by just putting more points on the right side. Okay. I can have more richer people earn more and the GDP will move to the right. Okay. So, it does not talk anything about the people who are below the poverty line. Okay. So, if you go only by the GDP, it tells you only one part of the story. The GDP are usually presented with the minima or the maxima, or with the not the minima or the maxima, but the minimal value and the maximal value and the bounds that govern it. Okay. So, that only gives you the entire story. So, Now, the question is, it is not enough if you just take the mean, but you also need to know what is the spread of the data. Okay. So, how can I measure the spread of the data? Okay. So, now imagine that this is the axis, okay, of these values of height, okay, and let me draw an average at 5.7. Okay. So, I am just imagining that 5.7 is the average, okay, it could be. Now, I am just going to say, there are 2 people at 5.8, 5.9, 6, 6.1, 6.2, there is some guy at 6.4, okay, some numbers 6.4, 6.2, 5.8. This is not to scale. Similarly, I might have someone at 5.5, 5.6, 5.3. So, I might have about like some 4 people, I might have about 2 people, I might have about 3 people and 5.3, something of that sort. Okay. Now, this average only gives me, see, this can also directly translate into a histogram if you look at it. This just tells you the frequency. Okay. If I have about n people, okay, how many of that n is at 5.7 or 5.8, how many of that is at 6, how many of them are at 6.2, how many of them are at 6.1. So, if you make these into rectangles, that will represent a histogram directly. It is just 90 degrees off this way, that is all. Okay. Now, the point is, in a relative sense is what I can come up with a spread. The other one would be the absolute value, but the one way of looking at how do I measure the spread is in a relative sense. So, the first moment that you have is your mean. So, now what I am going to say is this, on an average I expect the next person to be of this height. But if this person is taller, then I am going to see how taller, because it is a relative metric. Okay. So, what I am going to do is this, I might want this information. I just want to know this information. All the green lines are the distances of each of the point, each of the realization, each of the sample to its own mean, meaning this height, there is a mean height. So, how far is this realization from this mean will give me a spread data, but I will not have one value. I am going to have, if this we call it as the distance or the difference. Okay. For this point I have a difference, for this point I have a difference, for this point I have a difference. So, for 60 points I will have 60 differences. Now, I need to make this into a one metric, okay, and these are all distributed, these are all not at the same, obviously they are not at the same place. So, how do you do this under such situation? Have you heard about the word RMS, the phrase RMS? Root mean square. Okay. So, whenever you are faced with multiple outputs and you want to get a like a qualitative one quantity representation for that, you usually do the root mean squared. Okay. But why do you need a square? The distance can be positive or negative. Okay. So, that is the reason. So, what we do is this, we say xi minus mu. Okay. So, this is the distance, this is the green line that I have presented here, okay, squared, because this xi minus mu could be positive or negative. Why? 5.8 is an xi, the mean was 5.7, if I difference it is 1 or sorry 0.1. Okay. Whereas, if I did 5.6 minus 5.7, then it becomes minus 0.1. Okay. So, if you sum them up, they will even out. So, you do not want to do that. So, you penalize it. The more you are away from the mu, the more is a weightage for you. So, I square it and then it is going to be the sum of I running from 1 to n. So, this is squaring and I need to do a mean. when I divide it by n, I add them up and then I divide it by n, then it becomes square mean. Then I have to take a root, so that it goes back to the base unit that we spoke about. Okay. So, this is just a distance unit, so it will go back to the distance unit. So, this is what is the standard deviation. Okay. So, it is basically a spread of the data. Okay. So, oftentimes these two guys need to be discussed together. If I just tell you the spread of the data that I have is 10, is it good or bad? I have a data, I tell you the spread of the data is 10. Do you think it is good or bad? It depends on the average. Okay. So, usually we use the word called coefficient of variation, COV. Okay. So, what it says is it is sigma over mu. Okay. So, that is what he nicely said. He told this variation has to be compared with respect to the mean. Okay. So, let us take the case of sigma equal to 10. You cannot comment whether it is good or bad. You need to know what your mean is. If the mean was 100 and the standard deviation was 10, it is only 1/10 of variation. However, if my mean was 20 and my standard deviation was 10, it is a bad deviation, it is about 50% deviation. Okay. So, lesser the deviation compared to the mean in terms of the ratio compared to the mean, the better is your coefficient of variation. If it is a manufacturing process, your manufacturing process is better. Okay. If it is on some performance, it is a good controlled performance. Okay. So, usually the word the coefficient of variation is used and it makes sense, okay, to do it that way. And the other term that is usually used is variance, which is standard deviation squared. Okay. It is the square of the standard deviation. Okay. So, there were some questions on this yesterday and that is why I am going through this in detail. Okay. So, the next one that we, so is this clear so far? The mean, the standard deviation, and these are the two basic stuff that we will discuss in this course. That is all. There is something called signal to noise ratio that you need to discuss. For that, you need to know this information. Okay. The other one that I wanted to discuss is, yesterday I pointed out that you can normalize all the data. Okay. So, this is just a data analysis technique. It is not necessarily applied only in statistics. Tomorrow when you are trying to plot something, okay, there could be two variables x1 and x2. Okay. x1 can be measured in meters, okay, and x2 might be measured in microns. Okay. So, in that case what happens is, if you try to plot them in their actual values, okay, you know what happens if you are going to map meters with respect to microns. Microns is 1 e power minus 6. The deal is, you might want to normalize the data to plot it. Okay. Hence, what people usually do is they plot it between 0 and 1 in each axis, okay, or you can normalize one axis to log of that particular data. In a similar fashion, what we are trying to do in this case is, we are only trying to make the mean of any data equal to 0 and the standard deviation to 1. So, what we discussed yesterday is, we said Zi will become xi minus mu over sigma. Okay. The Z is the usual notation that is used. Is the usual notation that is used. Okay. So, the deal is, what is this going to do for you? That was a question that was asked. Okay. We will take a simple numerical example. Okay. Simple example. So, let us say your x is 2, 3 and 4. What is the mean? What is the mean of this? 2 plus 3 plus 4 divided by 3. Summation of xi divided by n, in this case n equal to 3. So, it is 4 plus 3 is 7 plus 2 is 9, 9 divided by 3 is 3. So, the mu now is 3. What is your sigma? sigma is going to be 2 minus 3 the whole squared plus 3 minus 3 the whole squared plus 4 minus 3 the whole squared. Okay. And then you have to take the n in the denominator, which is 3 the square root. Okay. So, this is going to be 1 plus 0 plus 1 divided by 3, which is 2 over 3. We will keep it like this. It is actually square root of 0.66. Okay. We will keep it like this. Okay. Now, what I am going to do is this, I am going to try doing this Zi. Okay. I am going to convert this x to Z. What I need to do? I need to do 2 minus, what is the mu here? What was the mu for that data? See, if you want to do, you can even make it like this, mu of x and sigma of x. So, what is the mu of x here? It is 3 divided by the sigma. How much is it? Root 2 over 3. Similarly, you are going to do 3 minus 3 divided by root 2 over 3. 4 minus 3 divided by root 2 over 3. Okay. So, if I want to find the mean of z, I just have to sum these guys up. What will it be? 1 divided by the sigma of x plus 0, okay, 3 minus 3 is 0 divided by the sigma of x plus minus 1, correct? What is 2 minus 3? Sorry, 2 minus 3 is minus 1 divided by sigma of x, that is nothing but root 2 of 3 plus 0 of sigma x plus 1 of sigma x, okay, divided by 3. What will you get? This guy will cancel out with this guy, this is 0. So, you will get 0 as your mu z, sorry. In a similar fashion, if I were to do sigma z, so what you do, you have to take this and find out what the standard deviation is. So, 1 divided by sigma x, okay, minus your standard deviation, sorry, minus your mean, which is 0. Okay. So, I need to take a square of that, right. So, I will say 1 over sigma x, I am not saying minus 0 because it is the same value, squared plus 0 over sigma x squared plus, okay, this is actually minus 1 over sigma x, right. So, plus 1 over sigma x the whole square. Okay. This is being retained the same because my mean is 0, the mean of z is 0. Okay. Now, I need to make a mean, then I need to make a square root. Okay. So, this will be what, if I do this, sigma x 1 plus 0, okay, or sigma x squared, okay, divided by 3. So, this is 2 by 3, okay, and times my sigma x squared. What will that be? This is 1, square root of 1 will be 1. So, what did I get? A mean of where did I start from? Okay. I started with a mean of 3 and a standard deviation of root 2 over 3 and I went to a mean of 0 and a standard deviation of 1. Okay. This is the standardization, but I can always get back these data. Okay. I can always go back from here to here. I just need to say xi is equal to zi times sigma x plus mu x. I will always know sigma x and mu x. I can reconstruct my xi, that is not at all a problem. Okay. Now, what is the benefit of going from the x domain to the z domain? Because now I can replace this 2 by 20,080. I can make this guy 34,500. I can make this 43,250. This is some numbers. You do the same process, you will get a mu x, you will get a sigma x. You go and then you subtract that mean divided by the standard deviation. You do again, you will get the mu z to be 0 and your standard deviation to be 1. Irrespective of the set of data that you have, you can always convert it to 0 and 1, mean and standard deviation. Okay. So, now in order to find the probability, I will deal only in the z domain, I will not deal in the x domain. Once I get the probability, it is easy for me again to go back to my x domain, because I just need to know only this information. So, in terms of the probability content preparation, I only need this guy for whom the mu is equal to 0 and the standard deviation is equal to 1. Okay. Okay. So, I just will have only one chart where the mu equal to 0 and the standard deviation is equal to 1. Any data, I will convert it into a data where the mean equal to mu, the mu equal to 0 and the standard deviation equal to 1, and I will be able to compute my probability. Then again I will go back to my x domain. So, this is the whole idea of that normalization. Is that clear? This was one thing I just told quickly yesterday, but there was question, so I am explaining it today. Is that clear? Okay. Yeah, fine. Okay. So, this is something that I wanted to tell. Do you have any questions? No. Okay.